Hello, and welcome to our only video covering the topics in section 2.1. In this video, we will be covering the topics of linear transformations and the matrix of a linear transformation. And big idea alert, there's some real meat in this video. All right, so linear transformations. Let's revisit the matrix vector product. So you remember that good old AX equals B? I do. Well, we can think of this in a new way. Something we've already actually done several times at this point. We originally had the row version of this, then we had the column version of this. Now we've got a new version, new way of thinking about this. So in this new way of thinking about it, we can think of the matrix A as a function that takes as input the vector x and outputs via multiplication the vector b. So A here takes vector x and spits out b via matrix vector multiplication. So in this new way of thinking about things, we can think of an n by m matrix A as a function from Rm to Rn. And if you need to pause for a moment and convince yourself that I didn't mess up the order of these m's and n's, and that indeed if A is n by m, then x is in Rm and b is in Rn, then go ahead and pause until you've convinced yourself that that's true. Okay, so I guess I'll call this the function version of the matrix vector product. And all right, this leads us into our first definition of a linear transformation. So there are lots of possible transformations, which is just another fancy way of saying function. But there are lots of possible transformations or functions from Rm to Rn. And here's a special kind. So the special kinds of functions from Rm to Rn, we call them linear transformations if there exists a matrix that can represent that transformation. So here, let me read this through properly. So a function t from Rm to Rn is called the linear transformation if there exists an n by m matrix A such that this transformation, if you plug in a random vector, then that transformation, whatever vector it takes x to, well, it's the same vector you would get if you multiplied A by that vector. And that this matrix A, it doesn't change depending on the vector. So it's a linear transformation. If any vector you plug in here, the transformation does the same thing as if you multiplied that vector by A. Okay, so that's a definition. So let's just use it for a second and see, okay, let's have an example. So suppose you have some vector in Rn, and you have some function t from Rn to Rn, defined as follows. T of x equals x. So what this is saying is that this transformation, you input a vector x, and you get that vector x back out. Is t a linear transformation? Which is asking, can this transformation, quote unquote, I mean, it's not really doing anything, but can it be represented by matrix vector multiplication? So is it linear? It sure is. Because consider the following n by n matrix. So here our matrix A is a matrix that has ones on the diagonal and zeros everywhere else. And let's see what A times a vector x does. Notice, all right, A times vector x. All right, I've just written it out. A here, vector x here. And notice that, all right, if we start calculating this product, the first row dotted with this vector will just be x1 times 1 and 0 times everything else. So, in fact, the first entry of the output vector will be x1. Second row times the vector, or dotted with the vector, we'll just leave x2 as the only thing that doesn't get killed by zeros, and so on all the way down to xn. So indeed, yes, if we do this matrix times this vector, we get this vector back. So AX equals X. And so it is true. This is a linear transformation because we found a vector that does the same thing. Note this matrix A here is special. I think I flagged this in a previous video, called it the holy grail of matrices, said we weren't done with it, and definitely weren't, and we're not done with it. We'll see this over and over again this term. A matrix like this, I think we first saw it in reduced row echelon form. Whoops. Anyway, a matrix of this form is called the identity matrix. So if you have an n by n matrix with ones on the diagonal, zeros everywhere else. And it's called that because in math, for whatever reason, things that do nothing are sometimes called the identity. So, for example, 0 is called the additive identity because adding 0 doesn't change anything. 1 is called the multiplicative identity because multiplying by 1 doesn't change anything. So here in matrix land, this matrix with ones on the diagonal, 0 everywhere else, is called the identity matrix because multiplying a vector by that matrix or matrix by the vector doesn't change the vector. So, all right. Yeah, here's a sad fact about this definition of linear transformations. It turns out this is not actually the best definition to use for linear transformation. Basically, all it had going for it, well, I mean, as a definition, what it has going for it is that we've been talking about matrices, so it's not totally out of the blue to talk about the matrix and a linear transformation in terms of matrices. But it's kind of difficult to use in practice. Like, how can you tell if a certain transformation can be represented by multiplication by a matrix? Like with the identity transformation, all right, I just handed you the matrix, but would you have come up with it by yourself? Well, maybe that one, and maybe there are a couple others that you could, but in general, it might not be trivial to find the matrix. And this gives you no hint about how to even go about doing that. So one thing that's tough, it's difficult to use in practice. It's also pretty specific. Like this definition only applies to functions from Rm to Rn. And so, so it leaves out lots of other scenarios where we might want to consider a transformation to be linear. And in fact, I'll discuss one a little bit later. So, like, turns out linear transformations, big idea in math, happens outside of this class in so many areas of pure and applied that it's, having it simply be defined as something that's representable by a matrix is too limiting. So here's an objectively better definition of a linear transformation. So a linear transformation, or a transformation T from Rm to Rn is linear if the following two things happen. First, all right, T times T, the transformation that takes as input, like vector V plus W, that's the same as just taking the transformation of V and adding it to the transformation W. So the idea is, I mean, I always kind of think of this as like the transformation distributing over addition, but that's not like really what's happening. What's really happening is it's saying you can either add vectors and then take the transformation, or you can transform the vectors and then add them, and you're going to get the same thing either way. So that's our first condition. We have a linear transformation if we have this like quote unquote distributing over addition. The second condition is that you can pull out a constant. So this is saying that the transformation of some vector scaled by k, that transforming the scaled vector is the same as transforming the vector first and then scaling. So both of these are sort of like, it doesn't matter what order you do addition, and it doesn't matter in what order you do scaling. And if you satisfy these two conditions, then then by definition, which seriously, almost every other book in the world uses this as the definition. Okay, if you satisfy those two conditions, you're in a linear transformation. What this doesn't have going for it is that it seems kind of out of the blue. Like why this? But let me give you some reasons to prefer this. Let's check. Is this identity transformation, is it linear? This gives us a method for checking. We don't have to be clever and guess what the matrix is. We just check. Well, all right, what is T of V plus W? Well, T of V plus W, well, because this transformation takes as input and just spits out that same thing as output. So that's just equal to V plus W. But then V is equal to T of V, right? Because X is equal to T of X. So V is equal to T of V and W is equal to T of W. And so, all right, our first condition is satisfied. T of V plus W does equal T of V plus T of W. Now let's check out that second condition. Again, T input is the scaled vector, but whatever. This identity transformation just takes its input and spits it back out. So that's just equal to K times the vector. And then we just said that, V is equal to T of V. And so, indeed, it is linear because we've satisfied both of these conditions. So, all right, great. This is useful because this we can check. We don't have to be clever. We don't have to be as clever, I suppose. Here's another thing it's got going for it. This is easily generalizable to all kinds of functions, not just functions from Rm to Rn. But here's like a crazy one. You can think of differentiation as a function. It's one where you say, have as input a differentiable function, and then it spits out another function as an output. So you could think of it as like, a function from the set of differentiable functions to the set of general functions. And then you can ask, okay, is it linear? That is an interesting question. And turns out, once you start getting these ideas of linear transformations going, suddenly a lot of the stuff that we're going to talk about in class is going to be generalized to just really kind of, it seems crazy. We'll generalize the notion of vector space and then generalize the notion of linear transformations. And then we'll see them all over the place in applications where we'll be really happy that we have this generalization. And, maybe not just in this class, but later math classes, it's so useful. This notion of a linear transformation is the one that gets used. Okay, enough waxing poetic about a definition. Here's a fact. The two definitions are equivalent if we're just talking about functions from Rm to Rn. And your book goes through a proof after theorem 2.1.3. But okay, all right, so we've seen two definitions of a linear transformation. The first one said the linear transformation is one that can be represented by matrix multiplication. The second one gives you a test for it, but neither one straight off the bat tells you how to find the matrix of a linear transformation. So let's discuss. First, we're going to take what seems like a little detour and talk about the standard basis for Rn. So let's start with something we know. Let's look at R2. So the standard basis vectors for R2, well, our first one is the vector 1, 0. This is sometimes called I hat, especially if you're in physics. In this class, it will be written vector E sub 1. And I think the E comes from Euclid, because this is like Euclidean space, but if that's wrong, you didn't hear it from me. Okay, so our first vector is this E sub 1, and our second standard basis vector, sometimes called J hat, is this vector 0, 1. which we will call e sub 2. All right. In R3, our first standard vector will be this one on the x-axis, 1, 0, 0. Then our second standard vector, E2, will be 0, 1, 0. And then our third standard vector, E3, will be 0, 0, 1. So these are I hat, j hat, and k hat. For those of you who like physics, like I do. That's all right. But all right, now let's talk about Rn in general. Well, the first standard basis vector in Rn is just going to be a 1 in the first position and zeros everywhere else. Second standard basis vector in Rn is a 1 in the second position and zeros everywhere else. And so on until you get to the last basis vector, zeros everywhere except, whoops, that should be a 1. I'll correct that and before putting the slides on Canvas. But who cares? Well, a linear transformation, it turns out, is completely described by what it does to the standard basis vectors. So suppose you know how you've got a transformation defined and you know how you've defined it for vector e1, e2, all the way up to en. So you've defined it for all of your standard basis vectors. Can you say what the transformation does to a general vector? Absolutely. So let's see why. All right, let's write this general vector, all right, x1 down to xn. And now we can kind of break up this general vector in terms of, scaling each of our basis vectors. And if you're at all skeptical, just try, multiply through and add these all up and you will 100% get this back, unless I made a typo. So yes, that is just, we can write x, any random vector x, as a linear combination of these basis vectors. You remember from previous video? So all right, now let's think about what is the linear transformation of x. Well, if I rewrite x in this way, and then remember the objectively better definition of linear transformation says I can pull out vectors and distribute over addition. So that is equal to x1 times the transformation of the first basis vector plus x2 times the transformation of the second basis vector, and so forth. And so, yeah, if I know how the transformation affects the basis vectors, then I can calculate what the transformation does to any random vector x. And yeah, this is because of our objectively better definition. So yes, a linear transformation is completely described by what it does to the standard basis vectors. And so is the corresponding matrix. So, okay, let's think about this for a second. Our admittedly less good original definition of a linear transformation said, okay, it's linear if it has a matrix, or if it's equivalent to multiplying by a matrix. So, okay, let's run with that and say the transformation times, or transformation of this vector e sub 1, that should be equal to some matrix A multiplied by e sub 1, which, all right, so let's write that out. We got some general matrix A times the first basis vector. And now do this matrix multiplication, the basis vector dotted with the first row. The only thing that doesn't get killed is A11. Dot this with the second row. A21 survives. So on and so forth, dotting it with the last row, AN1 survives. And so notice, if you do this matrix vector multiplication, what you get is the first column of matrix A. And in fact, in general, the matrix A times any basis vector e sub I, and this is just a random basis vector, that's going to be equal to T, the transformation of the basis vector. But since this matrix multiplication gives you the ith column of A, then the transformation of the ith basis vector should give you the ith column of A. So this is where we, this fact we are going to use. This is how we find the matrix of a linear transformation. All right, this is theorem 2.12 in your book. And it says, consider a linear transformation T from Rm to Rn. Here's the matrix of T. The matrix is what you get by making the columns, so the columns of your matrix are equal to how the transformation, what the transformation does to each basis vector. So the first column is the transformed first basis vector. The second column is the transformed second basis vector, and so on till the transformed mth basis vector. Now you might be a little bit grumpy with the fact that this still requires you to know how the transformation affects every basis vector. But I think this is actually not unreasonable, because if you're defining, if you know enough about a transformation to know that it's linear, say, you probably do know enough to say what it does to the basis vectors. And here, let me give you an example where maybe the rotation, that was a Freudian slip, where maybe the matrix is not obvious, but what happens to the basis vectors certainly is. So what is the matrix for counterclockwise rotation of R2 by 90 degrees? If you need any convincing that this is in fact a linear transformation, maybe go back to that 3 blue 1 brown video where he defines a linear transformation to be one that takes lines to lines and doesn't move the origin. And rotation about the origin by 90 degrees definitely satisfies that. But okay. So let's start with our basis vectors. So what our first basis vector, 1, 0, what does rotation by 90 degrees do? Well, it takes it to the vector 0, 1. So that, is our transformed first basis vector, is 0, 1. Now let's look at our second basis vector. Happened to be this one, but that was, that's just a coincidence here. So our second basis vector, 0, 1, what does the transformation do to that? Rotating by 90 degrees takes us to negative 1, 0. And so the transformation of our second basis vector is negative 1, 0. And now we have enough to write down the matrix of a rotation by 90 degrees. It's the first transformed vector, so 0, 1, times the transformed second, and then the second column is the transformed second vector, negative 1, 0. All right, a lot of good stuff in here. I will see you in the next video.